the molecule is straight. It can't bend at all. So it has a straight shape, which makes it somewhat rigid. And if you had a bunch of those joined, together in a food, they're going to kind of pack on top of each other. And that's why you can create a solid like this butter, or coconut oil, same thing. We also see it with the animal fats. Like, if you cook a piece of meat, when it's hot, the fat melts, but once it gets back to room temperature, you notice that it gets solid again. And so those are saturated fats that are in the meats as well. And so one thing about saturated fats is, one, they're very stable, because they don't have, they're saturated with hydrogen. So nothing else can attach to this molecule. It's completely full with hydrogen. So that makes it very stable. Like, the air can't really react with this because there's nowhere for it to react. In order for a reaction to occur, you would need a carbon that had a hydrogen missing and that had like an extra arm for something else to attach to it. And so that's not going to be the case with the saturated fat. It doesn't have that ability. So they're super stable. They can actually take some heat because of that. They tend to have higher melting points. So if you put them in a pan, you could crank the heat up to like a medium, probably like a medium to medium high. And it's not going to smoke. It's not going to go bad on you. It's not going to get damaged. And so saturated fats are actually, and I know this is contrary to everything we all have been told, but saturated fats are the best ones for cooking because they're stable. They're not going to go bad on you. So that would include things like coconut oil and butter. And then there's something called clarified butter, which is also known as ghee, which is basically just it's the oily part of the butter with all the solids removed. That's actually a really good cooking oil. It's good for veggies, by the way. Makes the veggies taste good. And then and palm oil. Palm oil is like a cousin of coconut oil. It's different type of palm tree. There's coconut palms, and then there's palm fruits, which are these little red looking, almost like a little apricot. But the inside flesh of the little palm fruit is reddish, and it has, if you press it, you get an oil out of it, just like you can press a coconut and get oil out of it. So it's a solid at room temperature, and it's a saturated type fat. And then these other fats, the ones that are liquidy at room temperature, this one is called a mono unsaturated fat, and it's called a mono because mono means one, and it has one location in the molecule where there actually is some hydrogens missing. And when that occurs, what happens is there's a little bit of a bend in the molecules. It's mainly because there's no hydrogens here to take up that space. So if there were, it would have to flatten out and straighten out. So, but because there isn't anything there, it just tends to kind of want to bend like that. And so that one location, there's actually two arms going between the carbons, and we call that a double bond. And the double bond, even though intuitively you might think, oh, that means it's stronger. There's two of them. It's holding it together there. That makes it stronger of a molecule. But in reality, it's weaker. It's weaker than the saturated fat because it's actually missing two hydrogens, which means that something can react with this. It can literally come in and try to react with this molecule and then damage it. So it becomes somewhat vulnerable now when it has a double bond. And when there's only one in the molecule, we call it a mono unsaturated fat. And because there's only one, if you look at this, you can see that most of the molecule looks very similar to a saturated fat, like this part and then this part. Like most of it is pretty well saturated. It's just this one spot right here that isn't. And so we say that these are semi-stable. You can cook with them at like low to medium heats. That's why you can use some olive oil at a low heat. Some other oils that are monounsaturated are going to be like avocado oil, macadamia nut oil. You've got sesame oil. I believe is in this category as well. And yeah, those are pretty well most of the monounsaturated fats that there. By the way, canola oil has that as well, but canola oil has other issues with it where it's actually less stable as well. So we're not gonna put canola oil in the healthy category. But you know, it's pretty good. And then we've got the polyunsaturated fat, which has 2 or more double bonds in the molecule. This image is showing 2, but there are some polyunsaturated fats, like for example, those that might show up in soybean oil or corn oil or safflower oil, sunflower oil, that there can be up to 6 locations along the molecule where there's a double bond. And then every time there's another double bond, it makes it more and more weak and more vulnerable, meaning that it really isn't good for cooking. If you heat it, it's going to get damaged. And so even though it's like complete opposite in our culture, we've been told that we need more of the polyunsaturated fats. We should avoid the saturated, use those polyunsaturated fats for all of your cooking purposes. And even though in foods, like in a seed, like if you eat seeds, if you eat nuts, if you eat grains, those polyunsaturated fats are what I call the good fats, because they're still in the food and they're protected. Once you press them out, they're now like away from their fibers, they're away from their antioxidants, they're away, you know, they're basically like naked. And then they're vulnerable to the light. You know, just the UV rays from the light can damage those double bond spots. And any kind of heat will definitely do that. One thing you guys will know, you'll relate to this. I'm sure you have seen this happen at one time or another with your cooking. If you put oil in a pan, if you've got your burner, and then you stick your pan right on top of the burner, and then your pan starts getting hot, and then you put your oil on the pan, and then you notice what starts happening with the oil. You notice that it actually kind of almost starts to move. Like you'll see it like shimmering before it would get too hot. Hopefully it wouldn't get so hot that it would start smoking. But there comes a point where it actually literally starts shimmering, the oil does. And why is it doing that? What's happening is you're literally raising the vibration of the connections between the carbons and exciting it. You're exciting those electrons that are in there. And so because heat is energy, so you're just like applying energy, heat to this, and it starts to actually move. Those little bonds start to move. Now, if it gets too hot, what happens? It smokes, right? So what is the significance of that molecularly? Well, molecularly, it's because you literally broke apart a bond in the molecule, and now you've got damaged oils. And here's one way you can know whether you've damaged your oil is when you're done cooking with your oil, it's brownish or almost black in your pan at the end. If that's the case, you know you heated your oil too hot and that it really damaged your oil, and you've probably got a bunch of free radicals now that seeped into your food, and that's what you ate. If your oil is still the same color that it was when you started with it, then you know you've kept it protected and it didn't get too hot. And that should be the case. It's a good visual, a good kind of rule of thumb. One little trick that I have to help with that is using a little bit of water. Let's say you're going to stir fry something. You want to cook some meat or something in some oil. If you put a little bit of water first in your pan, like here, here's your burner, there's your pan, and if you stick oil right on top of the pan, it's going to get hot really fast. And sometimes it's too hot too fast, and it's beyond the point of being able to save it. But if you put a little barrier of water in the pan and then put the oil on top of that, you're literally putting a barrier of water between the pan and the oil. And so water, when it boils, can only get up to 212 degrees. That's the boiling point for water, right? That's 100 degrees Celsius, 212 Fahrenheit. And so you protect your oil that way because you'll see steam coming off the water, but you won't see smoke coming off the oil. And you can tell the difference, and you can certainly smell the difference between steam and smoke from your oil. And your oil's protected, and then it's just kind of nice. Sometimes I just even try to use broth or water for the main cooking part of whatever, if I'm cooking some chicken or maybe some vegetables. And then I add the oil more toward the end of the cooking, more just to flavor it rather than actually using it for the cooking. That's if I want to use a polyunsaturated oil or a monounsaturated oil. If it's a saturated, it's okay. I can put it right on the pan and it doesn't really matter. So like when I cook eggs, I use coconut oil or ghee for that because I like to do a over easy egg sometimes. But for other purposes, I tend to use the water method, and it protects the oil that way. Let's talk a little bit about the trans fats. This is sort of the key of why trans fats are not healthy for us. So why are they bad? So here's a depiction of our polyunsaturated fat. And when it is in its natural state, it's got a little bend to it. And the two hydrogens on this double bond are on the same side. And if we go back to this image, we see that also they're on the same side of the molecule, and over here too, where the double bonds are, the hydrogens are on the same side. So in nature, that's the natural formation. And we use the prefix cis, CIS, which is a Latin prefix, which means on the same side. And so that's the natural way it exists in all of our foods. To make a trans fat, what has to happen is there has to be a chemical reaction that forces one of these hydrogens to flip to the other side of the molecule. And when it does that, what happens is it creates a straight shape within the molecule instead of that bend shape. And even though it's still a double bond and there's still hydrogens missing here on this bond, it's just that it now has changed the property, the physical property of that type of oil. So you've taken a liquid, normally these are liquid, and turned it into something that sort of resembles a saturated fat in terms of its shape is straight now. And so it turns it into a solid. So that's how you can take soybean oil, bubble hydrogen in, flip that one hydrogen over to the other side of the bond, and then you straighten it out. And now it looks like shortening. It basically becomes like lard or like coconut oil, and that's how they make Crisco. And so the problem with this is this doesn't exist in nature. So when these fats get into our body, they try to incorporate into our cell membranes. That's one of the ways we use fats in our body is incorporating them into our cell membranes. But our cell membranes require this configuration. They can't really do well with accepting this configuration, but they do get in there. They kind of get into our cell membranes and they kind of get stuck in there. It's kind of like putting a key that looks like the right key into a keyhole, and you can kind of fit it in there. But then when you try to turn it in the keyhole, it gets stuck, and because it's not the right key. And then if you turn too hard, you might break the key off into the lock, and now you can't even get the right key in. So that's kind of what happens with trans fats in our cell membranes, is they do make their way into the little receptors, and then they just stick in there, and then even the good fats can't get in. So they create a rigid kind of hard structure instead of a nice soft fluid structure to the cell membranes. And then this causes problems because now we can't get nutrients into our cells. Because it oftentimes blocks receptor areas within the cells. Thyroid hormone sometimes can't get into its receptor in the cell, so that can create metabolism issues. Cholesterol sometimes can't make its way into cholesterol is supposed to get into the cell membrane to keep it from getting too far apart or too close together based on temperature. So if the cholesterol can't get in, now the cell is kind of wobbly and it doesn't function well. And so that's why these trans fats have been implicated in things like high cholesterol levels, because if the cholesterol can't make it to the place where it's supposed to go, then it just starts circulating around in our body, and then it probably makes its way to the artery and then kind of gets stuck there. So that's one reason why trans fats are implicated in heart disease. And then they're also implicated in diabetes, because if you're clogging up cell membranes, then the glucose can't get into the cell, and now it builds up in the bloodstream. And diabetes is just that. It's too much glucose in the bloodstream, and then that becomes inflammatory, and it even becomes toxic. We know that diabetes, if people have too much glucose in their blood, it starts to affect their eyesight. It starts to affect their circulation. That's why they get neuropathies and retinal neuropathies, and even kidneys. I'm thinking of that, nephropathies. So it affects so many different things, these trans fats. And so the idea of it is, one, to remove those from the diet. Just don't even eat things that have them in it anymore. And then eat a lot of good fats, so that as these cells, we lose cells every day, they die off, and they need to be replaced by new cells. So when you make a new cell, you want that new cell that you make to be a healthy one, not another clogged up trans fat cell. So that's really the way to do it. It's just to stop eating them and start eating more of the good fats. Yeah, and there's another loophole. I mentioned the one about the MSG, the trans fat. The food manufacturers have one on trans fat as well. They can claim that their product has 0 grams of trans fat per serving, as long as the amount is less than half of a gram or more per serving. So, I'm sorry, less than half of a gram per serving. Yeah. So if there is 0.4 grams per serving, they can put a 0 there. And so that's why I always encourage people to read ingredient lists, because if there is trans fat in the product, they still have to put it in the ingredient list. So like, for example, in this particular product, I don't even remember what this is, but it does have partially hydrogenated cottonseed oil in it. But over here, it says 0 grams of trans fat. So if people weren't looking here, they would think, oh, there's no trans fat in this product. It could just be that it's less than half a gram. And let's just say it was 0.4 grams. Well, what if this person eats 2, 3, or 4 servings of this at once? Then they're literally at that, those trans fats are adding up, and they're going to actually become more than a gram. And one thing we know is that the National Academy of Sciences was commissioned back in 2005 to determine what is the safe level of trans fat in the diet. And their report came back saying there is no safe level. They do damage even in small quantities. So remember, they're doing damage on this cellular level, really small cellular level. So even if it had less than 0.5 grams of trans fat in it, it still is doing a lot of damage and havoc in the body. So just best to get rid of those.